Hello everyone, welcome to Reactify Labs. In this video, we will talk about version vectors and vector clocks. Version vectors and vector clocks. So, why am I not getting a capital V? Interesting. Okay, so let's see what version vectors and vector clocks are. But before I start, let me tell you that while in the process of discussing version vectors and vector clocks, you might think that they both are the same, but they are not. Towards the end of the video, like before ending the video, I'll talk about how they are different. Uh, and I'll explicitly explain why they are different, but hopefully you will understand while I talk about each of them. Okay, so mm, let's start. Let's see the structure that we are going to follow today. First, we will actually start with version vectors. We will talk first what are version vectors, then we will see how version vectors work. Next, we will see the advantages of using version vectors, and after that we will see the challenges or drawbacks associated with version vectors. After that, we will move to vector clocks, where again we will talk about what are vector clocks, how vector clocks work, after that advantages and challenges, and after that we will see with an example to show working of version vectors and vector clocks, and after that explicitly talking about similarities and differences. Okay, so this is what we will follow today. So first let's talk the theory, then we will move to see the example. Okay. And yes, before that, let's see what are the real world cases, scenarios where we might need it. So let's say there are different nodes, okay? Or let's take this example. For example, let's say there is a Google Doc that you are editing. You and your friends are editing at the same time. So, like your edit and your friend's edit, let's say you edited 1 second before your friend, then your edit should come before your friend, or your friend's edit should contain the latest value, right? So how does that occur? How does it know that okay, this edit is related to this edit, or this edit is independent of this edit? So let's say there is a line called I am a good person. Let's say somebody changed good to bad, okay? And let's say somebody else changed this. Let's say there was another line called I am fine, and somebody changed this fine. Let's say you wrote I am a good person, and somebody else just instead of good like strike through good and wrote bad, but somebody else changed this line fine, right? In this line nobody was working, so third person changed this line. So how does system know that this bad was related to this good and this fine is independent? Okay, how does the system know? So this is what is solved by vector clocks. Okay, so yeah, with that in mind, let's start. uh, so let's see what are version vectors. So version vectors, first, what it is. uh, First we will see the definition goes like version vectors are data structures used to track the version of data, used to track the version of data across multiple replicas in a distributed system. across multiple replicas in a distributed system. Okay. Each node maintains a version vector that records the number of changes or updates it has made. Each node maintains a version vector. Each node maintains a version vector that records the number of changes or updates it has made. That records the number of changes and updates it has made. Okay. So, what did I say? Data structures, version vectors are data structures used to track the version of data across multiple replicas. Okay. So, let's say there are 3 replicas for a data. Okay. Then each replica will have an array of integers. Okay. So, everything will have 3. Basically, it will be like this: something, something, and something. Something, 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 and something, something, and something. Okay. So, it means this one, let's say if this is node 0, this is node 1, and this is node 2, then this node, this value will be for node 0. Like every node will have the copy of the counter or this integer value that other node has. Okay. So for this node, the first thing is the value. Okay. First place is the value for this first node. For second node, like for number 1, this is the value which will again be with everyone. Okay. So whenever there is an update on this one, okay, the same will be updated here. Okay. How, we will see later. I was just giving an overview. Okay. What is the structure of it? Yeah, the same thing. A version vector consists of an array of counters, with each counter representing a specific node in the system. Okay. What did I say? It's an array of counters. As I said, for each node, let's say there are 3 nodes, it's an array of counters. It's an array of counters. Okay. With each counter representing a specific node in the system. Each counter represents a specific node. This represents node 0, this represents node 1, this represents node 2. Okay. For example, same thing. If you have 3 nodes A, B, C, the version vector might look like, let's say 2, 1, 3. Okay. Where each node shows how many changes that node has made to the data. So node 0 has made 2 changes, node 1 has made 1 change, and node 2 has made 3 changes. Okay. Great. Now, okay, let it be here. Next, let's see how version vectors work. How version vectors work. So, first step is initialization. Initialization. When a distributed system starts, each node's version vector is initialized with zeros. Okay. So in the beginning, it's all 0. So yeah, if we start with, let's say for example, 3 nodes A, B, and C. So initially it will all be 0. Okay. Next step is making change. Making change. So each time a node makes a change to the data, it increments its counter in the version vector. So if node A, let's say, updates the data, then it will become 1, 0, 0. Okay. Right now it's just a very high level. I'll talk in detail about it in the later part of this video. And third step is synchronization. So when nodes communicate or synchronize, they exchange version vectors. Each node then updates its version vector to include all changes it has seen. For instance, if node A's vector is now 1, 0, 0, okay, as I told you, each node will have the same copy. Okay. Initially, all of those will start with 0, 0, 0. Okay. A, B, and C. Then B updated. B will do this. Okay. Now, after synchronization, when these will synchronize, what happens is, for both these vectors, for both these A and B, A will become 1, 1, 0, and B will become again 1 1 0. Okay, this is what A and B will become, because they will synchronize and they will exchange the data. The A will see that yes, B has updated, B has done some changes, so it should be 1, and B will see that yes, A has made some changes, so B will update its portion of the A. Okay, so that's it. That's how the version vectors work. Okay, now let's see the advantages of version vectors. Advantages of version vectors. So first is conflict detection. Conflict detection. So they help in detecting conflicts by comparing version vectors. If let's say two replicas have different version vectors, it indicates that they have diverged and may need to reconcile changes. Means, so let's say for node B, this is like this, and for node A, this is like this. Okay. Now it sees that yes, they have different changes, right? So they need to reconcile. Means A does not have, let's say this was with B and this was with A, it means B does not have A's changes and A does not have B's changes. It means there is a conflict and they need to reconcile. So this is conflict detection. And next is simple concept. It's very simple. It's just a counter increment, right? So simple concept. They are relatively simple to understand and implement, especially when dealing with data replication scenarios. Okay. Next, let's see the challenges. So the challenges associated with this is scalability. Scalability. As the number of nodes increases, the version vector grows in size, which can become cumbersome to manage, right? This size of array will increase, and synchronizing with each node becomes a challenge. And next is limited to data versions. Limited to data versions. So they are specifically designed for tracking data versions and might not be suitable for tracking more complex scenarios involving multiple events. Like, as I said, for A, let's say this is this. For B, let's say this is this. For C, let's say this is 0, 0, or let's say C and B have already synchronized. So this is this. Means not already synchronized, it means C has B's synchronized data, but B does not have, let's say, or actually initially C was this, C synchronized with B and C got this, and after that C updated. So it becomes 0, 1, 2, right? So what version vectors do is, version vectors only talk about the data versions. When they meet, they will only see that, okay, C has the latest changes. Okay, C has made the latest changes. That's it. They will not know in any way that, okay, the order of change was first A made, then B made, then C made. This will never be known. Okay, so this is the drawback, or the what do you say, one thing that is not possible with version vectors. Okay, so you might have understood it by now. What is this? It's limited to data version. Again, I'm saying this. So data version means A has some version, B has some version, C has some version. Yes, initially all these were independent, but then B and C got synchronized, and yes, initially C got 0, 1, 0. After that C updated. Now C and B synchronized, so B becomes 0, 1, 2. Now what happens is C and A synchronize, so C becomes 1, 1, 2. A also becomes 1, 1, 2. B also becomes 1, 1, 2. Okay, all of these synchronize, they all update, but still what they only talk about is which one had the latest version. They got to know that yes, C had the latest version. So since C had the latest version, all of them updated them to C. Okay, but nobody talked about how this version was related. If A updated first, or B updated first, or C updated first, or something else happened. Okay, or let's say A did something. A did, let's say, some event A, or A did some event X, B did some event Y, C did some event Z. In what order did X, Y, and Z happened? They only talk about, yes, Z was the latest version. Okay, so this is a drawback associated with version vectors, which is solved by, or which is taken care of by, vector clocks. So let's talk about that. So vector clocks. So what are vector clocks? So vector clocks are again data structures data structures used to track the causal relationships. Used to track the causal relationships. I know a lot of people read this as casual relationship, but I assure you it's not that. So, vector clocks are data structures used to track causal relationships between events. Between events in a distributed system. Okay? In a distributed system. They help determine the order of events. Okay? Something which was not possible with version vectors. They help determine the order of events and whether one event happened before or after the other. Happened before or after the other. Okay. So this is what vector clocks do. Now let's see the structure. The structure of vector clocks is similar to version vectors. They are also array of counters. However, in vector clocks, these counters are used to record the number of events at each node rather than just data updates. Okay. So again, if there are 3 nodes, all of them will have like these actually A, B, C. All of these nodes will have something like this, where each one will have a copy and each one will update its own counter. Okay. So it's nothing different. And as I had warned you in the beginning of this video, you will start feeling like they both are same, but they are not. How? Let's move forward. How do vector clocks work? So again, vector clocks also work in the same way as version vectors. First step is initialization. Again, each node starts with a vector clock initialized to zeros for all nodes. For example, nodes A, B and C all will have initial values 0. Okay. Next, processing events. Processing events. Whenever a node processes an event, like sending or receiving a message, it increments its own counter in its vector clock. So if node A processes an event, this will become 1, 1, 0. Again, same as version vectors, right? Yes. Let's see next. Next is event exchange. Event exchange. When nodes exchange messages, they include their vector clocks. Okay, same as version vectors. The receiving node merges the incoming vector clock with its own by taking the element-wise maximum of the counters. For instance, if node A, let's say, has 1, 0, 0 and node B, let's say, has 0, 2, 1, after merging, both of them will become 1, 2, 1. Still the same, right? So what is the difference? We will see later. Now let's talk about the advantages of vector clocks. I know I am testing your patience by saying that we will talk about it later, but trust me, we will talk about it later. Let's finish the theory first. Advantages. What are the advantages of version vectors? First is detailed causality tracking. Detailed causality tracking. They provide a detailed view of the causal relationship, not the casual relationships between events, which is useful for understanding the order of operations and interactions in distributed systems. And next is versatility. So they are applicable in a variety of scenarios beyond data replication, such as message passing as well as event ordering. Okay. Then, since they are more sophisticated, they must be facing some challenges related to complexity. As I have talked about this in one of my earlier videos as well, the more sophisticated your system is, the more easy it is for users to use, or the more functionalities it is providing to your users, the more complex its implementation is, right? A bicycle is more complex, a car is more complex to make than a bicycle, right? Because car is more sophisticated, car is making the lives of people more easy than a bicycle. That's why a car is more complex than a bicycle, right? So that's the same thing that goes with software as well. Next is scalability. Similar to version vectors, vector clocks can become large and unwieldy as the number of node increases due to the growing size of the counter array. Same thing, if the counter array keeps on growing, this will become a scalability challenge. Okay, great. Now that we have finished the theory, let's see the example of how version vector is different from vector clocks. Okay, so we will start like this. um Example. Okay, so as I said before, initially ABC, they all will be 0 0 0. Okay, let's say A increased 1 0 0, B increased 0 1 0, C increased 0 0 1. Okay, now what happens is AB synchronize and they become 1 1 0. BC synchronize, they become 0 1 1. Or actually AB synchronize, they both become 1 1 0. And now B and C synchronize, then C also becomes then actually wait, at that time C was 0 0 1, right? Now BC synchronize, they both become 1 1 1 and 1 1 1, and then this is still 1 1 0. Now they both synchronize, they all become 1 1 1, 1 1 1 and 1 1 1. So what they are doing, as I said before as well, they are just seeing which one has the latest version. Okay, which one has the latest version, and the one that has the latest version is the one which is the one which others will follow. Others will see that okay, this one has the latest version, and that will be followed, right? So that's it. This is the simplest way you can understand this version vectors. Okay, let's keep it aside for a moment. So let's actually let's do it like this. Keep it aside for a moment. Now let's see the vector clocks now. Okay, vector clocks are a little more sophisticated than version vectors. So what happens here is, let's say there are three processes, P0, P1, P2. I am taking this example from Geeks for Geeks. So there again, three processes, P0, P1, P2. Everyone will have initially 0 0 0, right? So let's say this is the timeline of each. What happens is there is an A. Okay, this A has 1 0 0. So something happened. Basically this is what this point A was, something happened at point A. Okay, and P0 did something, so it incremented discount. So basically we will follow this one here. So if something happens, like some event, counter updates means let's say the version vector is V. So for the process I, Vi becomes Vi plus 1. Okay, if some process sends something, okay, send, if it's a send event, again for that process Vi becomes Vi plus 1. And if some process receives something, then again for that process Pi, Vi becomes Vi plus 1. Okay, so this is what we will follow. Okay, then some event happened here, it means it became 1 0 0. Now at this point, let's say here something else happened, so again it will be incremented 2 0 0, right? Next, let's say at this point something else happened, but before this P2 did something else. What P2 did here is 0 something did, so it's 0 1 0, right? And now let's say they are trying to synchronize. Okay, so what happens when they synchronize? Okay, so what happens when they synchronize? So basically, this will send its data to P0 and P0 will send its data to P1. So let's assume that it did not do anything here, it will just send its data. So that's why it became 0 1 0. So actually let's go back a moment, and so P0 did something, so it became 0 1 0, right? Now P0 wants to synchronize with P1. So B will send something to, so P0 will send something. So B is a send event. So it will become 2 0 0, right? Because send is again something plus 1, right? Now B will send to this P2 or P1, right? At the same time, this one also tried to do something. So this one also wants to synchronize with P0. Both of them want to synchronize together. So it became 0 1 0 because again it's a send. So for P1 the send is again Vi is V1. So this one tries to send. So let's say it receives at this point, it receives at this point. So what happens here? So P1 receives, right? P1 sends, right? So P1 sends, so it became 1, and P0 receives. So again for P0, 2 will increase to 3. Okay, and this 1 will come here, 1, and this will become 0, right? Because what happened? When 0 1 0 came to P0, means P1 sent its data to P0, P0 got incremented, P1 got incremented here before sending, okay? P1 will not increment at this point. In any array, let's say for the process, if the process is P0, only V0 will update. If the process is P1, only V1 will update. Like P0, P1 is here, even if it was A, B, C, the way the vectors are allocated to them, only that will update, okay? Next, when this comes here, what will happen at that time? Tell me. So what happens here is P0 was sent, and since it was a send event, that's why it was increased. It was increased to 2. So the 2 will remain as it is, right? Now this one was already 1. Because of the send, it had increased already. Now because of the receive, it will again increase. So it will become 2 and it will become 0, right? Right. Next, let's say something else happens. Some event again happens here. So when some event happens here, it will become again 3 will increase to 4 and others will not change because others don't belong to P0, right? And meanwhile, what happened at P2 was some event occurred at P2. So when P2 occurred, then 0 0 0 of P2 will become 0 0 1, right? Right. Next, P2, let's say, decides to synchronize with P0. P2 decides to synchronize with P0. Then in that case, what happens is, here P2 decided to synchronize. So P2 decides to synchronize means this one will increase again because of the send event, right? So this will become 0 0 2, correct? And when this goes here, it decides to synchronize with P0, it means it goes here. And if it goes here, the 4 will remain as it is because, no, sorry, the 4 will increase because P0 is receiving. Since P0 is receiving, 4 increased, and nothing else should change, right? Second one is 1, correct? Second one is still 1. And third one is 2 because 2 is coming. So this became 5 1 2. So you might ask why this here it is 2 but here it is 1, right? For P1, in the P1 the second column or the second section is 2, but in P0 the second section is 1, right? 4 1 0. Here it is 2 2 0. In P0 it is 4 1 0. If you compare these two, this and this, right? You might ask this question. But if you see, after this became 2, there have not been any synchronization. If the synchronize was there, then only this one would have updated to 2. This one would have updated to 2. But there had been no synchronization. Okay, now how do I delete it? Because there was no synchronization, it has not updated yet. There was the earliest synchronization that has come is here. But this was between P2 and P0. That's why the second one, the middle one, is not updating. Okay. Great. Now, let's say now P0 and P1 decides to synchronize. Now, if P0 and P1 decides to synchronize, it means P0 decides to send something. So 5 will become 6, right? Others will remain as it is. Okay. And P2, sorry, P1, what will happen to P1? This will come, P0 will come to P1. And when P0 comes to P1, what happens is 6 will not change, right? 2 will not change, right? Something else will change. What will change? This 2, because it had this value 2, this will change. It will not consider this 1 because this 1 is older than this 2, because this one is smaller than this 2. So this 2 will get incremented by 1. Why? Because of this receive event. Okay, because of this receive event, this 2 will increase to 3, right? And again, let's say some event happens, then it becomes 7, 1, 2. You might still be wondering why there is 1 and why there is 3, because P1 has not synchronized with P0 yet. Here P0 synchronized with P1, right? P0 sent its update to P1. P1 has not sent its update to P0 yet. Now let's say P0 decides to, or P1 decides to send its update to P0 at, let's say, this point. Then what happens is, at this point it decides to send it this. So 6 will remain as it is, 2 will remain as it is, 3 will increase to 4 because of the this send event, right? The send event will increase 3 to 4. And how will this increase? This 7 is now receiving, this P0 is receiving, so 7 will increase to 8. This 2 will remain as it is because P2 is not involved, and this 1 is not considered. Here it's 4. So this 4, 1 will become 4. Okay. So this is how it is. So depending on the like the order in which it's synchronized, the events get updated. Okay, the value of the counter gets updated. Now if we name them, let's say this is C, then this is D, this is F, G, H, this is K, this is I, this is J, this is L, this is M, and this is N. Okay. Now what happens is, now we have to see, and actually not see, we can gather from here what events are causally related events. How do we tell that? Causally related events. Okay. So for causally related events, what should happen is the vector should be like this vector. If there is a vector v1, okay, this vector v1 is less than v2. Okay. So if this vector v1 is less than v2, means at least one, okay, at least one, there should be at least one I. So vi, which should be less than v2j, or actually v2i, same, not v2j, it should be same. Okay, so this is what causally related event is. Actually, before that, let's talk about a few more things. So when is v1 equal to v2? So we have two vectors, right? So this is vector. If you see the vector at p0, let's say p0 is v0, p1 is v1, p2 has the vector v2. So the same thing, the final value of the vector at p0 was 842, final value at vector this was 642, and final value at this vector was 002, right? So these are vectors, these cannot be directly compared, right? So how do we know that if any vector vi or any vector, let's say, let's name it anything for the sake of simplicity, let's take it v1, v2. How do you know that if v1 and v2 are equal? If every vi is equal to every v1i is equal to v2i, then only they are equal, right? Next comes, how do you say v1 is less than v2? If every v1i is less than every v2i. Okay, but if let's say there is something like v1i, some v1i is less than v2i, and there is some one, any one which comes, which let's say some j is greater than v2j, then in that case it's not small. Okay, everything should be small for it to be smaller. Okay, and for smaller than equal to, it should be v1i is less than equal to v2i. It means all the things can be smaller. Okay, smaller or equal to, not more, smaller or equal to. Let's say there are 10 elements that can be contained in this. Even 9 are equal, still at least one, if any one is smaller, it means this condition is satisfied, v1 less than equal to v2. And if all are smaller, then it's v1 is less than v2, right? So this is what this is how vectors are compared, right? Now if we see the causally related events, what do we actually, let it be, okay. Now two events which have timestamps, let's say again v1 and v2, how do we know if they are causally related, right? So if they are causally related, it will be like this: v1 is less than v2, okay, if and only if v1 is less than equal to v2, okay, and there is some j, and there exists some j such that j is again like that I, okay, let's, for the sake of simplicity, we have been using I, let's use I. There is some I, okay, for that v1 of I is less than v2 of I, okay. There exists some I, like anyone, even if one is there, it's fine. Others can be equal, right? For example, let's say if we have this two kinds of vectors, let's take any one example from here, okay. So there is one, it's this 410, so 410, and there is another 220, okay, 220. So if you see here, 4 is greater than 2, okay, 0 and 0 are equal, but 1 is where is it, okay, 2, but 0 and 0 are equal, but 1 is not less than. So here it does not satisfy this v1 less than or equal to anything, right? Because this is not right. Next, let's say if we compare 410 and 010, in this case if you see, 4 is greater than equal to 0, 1 is actually 1 is greater than equal to 1, it is equal to, but it can be said that, right, 1 is greater than equal to 1, or 1 is less than equal to 1, right? So it is like this, and again 0 is less than equal to 0, right? So this condition is satisfied here. So what we can say here is, if we have two examples, let's say there is an event called A. So what is the vector of A? 1 0 0, and there is something j. For j the vector is where is j? 220, okay. So if you see, A is less than equal to j, right? A is equal to j here, A is equal to j for the last one, but for others A is less than j. It means A and j are causally related. Means A and j are causally related, right? Let's take any other example now. So for example, let's take D, okay. So D is 410, and what one was this? This was, I believe, there is no event here. K, actually, okay, let's take K. So K is what? 642, okay. So in this case what happens? Again, if you see, 4 is less than 6, 1 is less than 4, 0 is less than 2. It means again D and K are causally related, right? It means D happened before K, we know that for sure, because D is less than K. Let's take some other example which are not related like this. If we take an example like 220, J is 220, okay, and something else like G is 612. Now if you see, 2 is smaller than 6, 0 is smaller than 2, but 2 is not smaller than 1, right? So in this case what happens is, we can say that they are not causally related. They are not causally related because they have not synced. We do not know what had happened before them, or we do not know how they are related, right? So that's why we can say that they are not causally related. So now I hope you understand what is the difference between version vectors and vector clocks. Version vectors are just doing this thing where they are just comparing the version, latest version, but vector clocks are trying to get the latest or the ordering of events. They are trying to get the partial ordering of events. They are trying to find the causal relationship between uh, different kinds of events. So now you might ask, if they both have the same data structure, if they are both using the counters, why do we need two things? Why do we have version vectors and why do we have vector clocks? Why cannot version vector do the same thing as vector clocks? Right? This is not an unreasonable question to ask. So as I started with the in the structure, as I stated in the structure, let's now see the similarities and difference and why do we have two data structures here. Okay, I don't have an answer to why, but let's see how they differ actually. If they both have the same data structure, same array of counter, why could not we suffice with only one? Okay, so both version vectors and vector clocks use a data structure that is an array of counters. Okay, which is also called vector. Each element in this array corresponds to a specific node in the distributed system at each, and the value at each index represents the logical time or version numbers for that node, right? So while the underlying data structure is the same, the implementation techniques, meaning how these data structures are used and interpreted in different contexts, are where the differences lie. Okay, even though the data structures are same, how these data structures are implemented, that's where the difference is. So if you see again, the version vectors are primarily used in replicated data systems to track which updates have been applied, right? The focus is on understanding where one version of data has seen all the updates from another version, right? Merging versions often involves taking the maximum of each counter. That's it, right? So, but for version vectors, they are used to track causal relationships. The focus is on causality and everything. But what is the key difference in the usage? So if you see the key difference, which is obviously partial ordering. So version vectors are used when you need to track versions of replicated data. So track versions of replicated data and resolve conflicts. That arise when multiple replicas have been updated independently. Okay, but vector clocks are used when you need to track causal order of events across a distributed system, ensuring that you can determine the sequence of events. Okay, so you might say again, I have been saying the same thing again and again. Why am I having a different section if I had to talk the same thing which I have talked earlier in this video? It doesn't make any sense, right? Yes. Okay, but I would like to conclude with one thing. How do you implement a graph? I'm talking about a normal graph data structure in which you apply this DFS, BFS. You can do like, what do you say? You can do it like this. If you see like this, right? You do it like this. So adjacency list is what is the most efficient implementation of graph. But there is an array implementation also, right? Array implementation of graph. Array implement. So basically, if we have, let's say, n nodes, then we make an n by n two-dimensional array, and that's how we implement a graph, right? And we have a data structure called array, right? We have a data structure called priority queue, right? We have a data structure called stack. We have a data structure called queue. We have a data structure called graph. If you see, underlying implementation of all these is array. So now you might ask, why do we need all different data structures? Why couldn't array suffice them all, right? But that is not the case here. Each of them specializes in different things. Similarly, both the version vectors and vector clocks, even though their implementation is same, array based, counter increment, still they both serve different purpose, and that's why we have two different data structures for different kinds of things. One is specifically for managing the versions, and other one is specifically for tracking the causal relationship. So I hope this last one convinced you why version vectors and vector clocks are two different things and not the same thing, right? So yeah, I can see this video went very long. So that's the end of this video. um, I hope this gives you a good understanding of version vectors and vector clocks. If you have any doubts, please let me know in comments, and I would say please watch this video again, at least the example part. Please rewatch it. If you haven't understood it, you will understand. I have put so much effort in explaining it at very ease, so that nobody should feel left out. I'm sure you will understand. Okay. So still, if you don't understand after watching a couple of times, please let me know in comments. I'll try to explain as in as simple way as possible after that as well. Okay. So I hope now you know a lot of theory about this version vectors and vector clocks, their examples with example implementations. It's also clear to you how both work, why they serve different purposes, and what are the advantages and challenges associated with each of them. Okay. So yeah, that's all there was in this video. Thank you for watching. Please remember to like, share, and subscribe. I will see you in the next one.